Welcome to Similar Polygons. I'm Mr. Pi, the math guy, and as you can see, we're going to be talking about and solving problems that have to do with similar polygons. So let's go ahead and get this party started. Similar polygons. Similar figures. Similar figures have the same shape, but not necessarily the same size. So in relation to congruent, where it was the same shape and the same size, similar figures have the same shape, but not necessarily the same size. Two figures are similar if the corresponding angles are congruent and the corresponding sides are proportional. So they're similar if the corresponding angles are congruent and the corresponding sides are proportional. The ratio of the lengths of the sides is the similarity ratio. What I do want to mention about that is that we would consider that to be the simplified ratio. The simplified ratio meaning something like 3 to 6 or 3 over 6 would have to simplify or reduce to 1/2. This would be the similarity ratio, not 3 to 6, but 1 to 2. Example 1, understanding similarity. Triangle ABC is similar to triangle XYZ. First thing you should know is this is the sign for similar. It's the top of the congruent symbol. So in this case, we're told that triangle ABC, triangle ABC, is similar to triangle XYZ. As the same as with congruence, with similarity, the order of the vertices is important. That means that angle A corresponds to angle X, or angle A corresponds to angle X. Angle B corresponds to angle Y, and finally angle C corresponds to angle Z. So if we're asked to complete each statement here, in this case, the measure of angle B would be equal to the measure of angle Y because they are corresponding angles, so the measure of angle B would be 78 degrees. Also, if triangles are similar or polygons are similar, the corresponding sides are proportional. So in this case, we're given that side BC corresponds to YZ, or BC to YZ. What side corresponds to side XZ? This side down here. Well, that of course would be AC. And what's important to note is that the order really of these vertices is important. Since XZ went the order X then Z, when I write down AC, it should be in the order AC. CA technically would not be a correct answer. Example 2, determining similarity. Determine whether the parallelograms are similar. Explain. Well, if we start with the sides, you don't have to start with the sides, but if you start with the sides, we're going to go with AB corresponding to JK. So that would be AB over JK. And that proportion or that ratio should be similar to BC to KL. And that would also give then CD to LM being equal to AD over JM. And filling in the numbers, we get 2 to 4, we get 1 to 2, 2 to 4, and 1 to 2. And in this case, the similarity ratio would be 1/2. Since these are all equivalent, they all simplify to 1/2. The sides are proportional. Now, if we take a look at angle B corresponding to angle K, corresponding angles should be congruent, and since the measure of angle B is equal to 120 and the measure of angle K is equal to 100, these two quadrilaterals, or what appear to be parallelograms, are not similar. And that's the symbol for similar. They are not similar, and that would be because corresponding angles are not congruent. So there we determined whether they are similar, they are not, and we explained that. So there's example 2, determining similarity. In example 3, using similar figures, we are asked to find the value of the misspelled x. That's this x down here. It has the green underline. You're probably used to seeing in a Word document if you misspell something. So that's what we're trying to find, is the length of segment xy. So we're going to put that here. This is a proportional reasoning problem because it's dealing with similar figures, and we have to identify or find the length of segment xy. So I'm going to put that in the numerator here. And in the denominator, I'm going to put its corresponding side in the smaller triangle. So that would be side RS. In the larger triangle, I have side ZX. And in the smaller triangle, I have the side ZR. So I'm going to fill in the numbers. I'm going to caution you where you might make a mistake. XY is what we're solving for, designated by X. RS is given as 4.5. XZ, here's where a lot of kids make a mistake. A lot of kids put a 6 in right here. Well, that's not the right thing to put in there. The distance of XZX is going to be 8 plus 6, which is equal to 14. It's the distance from ZR and then from R to X. So that would be 14. And the length of ZR is 8. So now we have a proportion to solve using cross products. 8 times x is 8x. 14 times 4.5. 5 times 4 is 20, carry a 2. 2 times 5 is 5, or 5 times 1 is 5, plus 2 is 7. 4 times 4 is 16, carry the 1. 4 times 1 is 4, plus 1 is 5. It was a 63. Not an 83, but a 63. Divide each side by 8. And I know 8 goes into 63 7 times, with a remainder of 7, so 7/8. A golden rectangle is divided into a square and a smaller rectangle that is similar to the original rectangle. Here, I have a pretty classic diagram or picture of golden rectangles, and what I'm going to do here is I'm going to pull them apart. Rotate this one around. We will see that they are all similar and nested inside one another. And all of these rectangles are golden rectangles, which have a ratio of length to width of 1.618 to 1. So the length to width ratio here is 1.618 to 1. And that's a pretty classic thing in architecture because it's known to be pleasing to the human eye. We're going to solve a problem with that coming up soon. Example 4, real-world connection. The dimensions of a rectangular tabletop are in the golden ratio. The shorter side is 40 inches. Find the longer side. Well, in this example, since we're dealing with ratios and equal ratios form a proportion, we're going to be working with a proportion. It tells us that the dimensions of a rectangular tabletop are in the golden ratio, which means it's a 1.618 to 1 ratio. Longer side to shorter side. Then it tells us that the shorter side of the table is 40 inches. Find the length of the longer side. Well, to solve this proportion, we simply end up multiplying 1.618 by 40. Eight times 4 is 32. Carry a 3. 4 times 1 is 4 plus 3 is 7. 4 times 6 is 24. Carry the 2. 4 times 1 is 4 plus 2 is 6. And this number should have 3 decimal places because 1.618 has 3 decimal places. So that gives us 64.72, and that would be inches. And 64.72 inches is very close to 64 and 3/4 inch. That'd be 0.75. So we could estimate here and say about 64 and 3/4 inches. Example 5, a real-world connection. A painting is 24 inches wide by 36 inches long. The length of a postcard reduction of the painting is 6 inches. How wide is the postcard? So we're told the length, we have to find the width. So what we're comparing here is the width to the length. And since it's a ratio and we have 2 of them that are equal, it's going to be a proportion. We're told that the painting is 24 inches by 36 inches. And we are told that the length of the reduction is 6 inches. So the length is 6 inches. What's the width? Well, this should be a pretty easy problem for you. And the reason I say that is it's a simple reducing a fraction. 36 can be divided by 6 to give 6. So if we take 24 and divide it by 6, it'll give us 4. So the postcard is 4 inches wide.